black flag and the descendants on there. I had to use that picture because of that. Anything give us grief in here, either text or extra. We got some exponential modeling. This was the McDonald's experiment, essentially, modeling coffee at a certain temperature, heated up at 180 degrees ish. I remember Andrew said it was 215 or 210 when that lady burned herself. So here's 180. And then the idea of this problem was to have you analyze the data on, there's a famous case from back in the 90s, I think we figured out it was in the 90s, when a lady spilled coffee in her lap at McDonald's and then sued. Right, so this is analysis of hot coffee and how it cools. So when somebody I did this morning, pours hot coffee into a pot, it's at a certain temperature. And eventually, whatever that temperature is, the coffee will cool down to what temperature? Room temperature. Can't get any colder than room temperature because it's going to come to equilibrium. But what's cool is the way it gets there. That's the interesting part because it's not linear. It's not like every minute it drops 2 degrees. It doesn't work linearly. You could act like it goes linearly very easily. You could say, okay, well it starts at 179 and goes to 100. That's 80 degrees over 50 minutes. 80 divided by 50 is what, 1.6 degrees per minute. You could do that if you wanted to, but that wouldn't be correct because it loses temperature, or loses temperature, I guess, more quickly in certain places and more slowly in other places. And that's what this was having you do here, and then analyze how long till it gets safe. How long till it's safe, and somewhere down there is safe according to the ADA or according to the Food and Drug Administration, FDA. Anything? Give you grief? Nah? Pretty straightforward. I tried to be pretty thorough with explanations on this because it's not the easiest mathematics, especially this one when I asked what percentage rate the coffee cools. And that's tricky because in class, when we were building our exponential models, we built them in steps. We built them as like x equals 1, 2, 3, 4, 5, 6, 7. So we could just look at the y values and figure out what multiplication was happening each time. And there were a couple of them. With the coin flips, it was a decrease by half each time, 0.5, 0.5, 0.5. With the population of the US, it was an increase of 1% each time, so 1.01. This one's trickier because it doesn't stair-step linearly. It goes up 5, up 3, up 3, up 4, up 3, up 4. So you have to keep that in. And I think I explained it pretty well down low, and you can see what's going on. Anything? Completely clear. I'm that good. I mean, I know. Don't want to brag. Fair? Maybe you need a chance to look at it yet. That's fine too. Make sure you do though. Make sure you do. There's a logistic thing tucked in down here, public debt, and then you got the answers down here. There's the equation you end up with. There's the equation you end up with right there, as far as the coffee temperature. Cool? Decent? Any questions? Your quiz, Kristen, thanks again for asking about it. The quiz that's due Wednesday is tied to this. It's tied to rolling dice, but you're going to roll your dice with the TI. I actually brought dice for us to roll today for probability, but you're going to roll dice with the TI and simulate basically rolling a big handful of dice and then taking out certain ones and then rolling the remainder again and then pulling out and then roll until you're down to 0. And then you have to deal with that data and take a look at how it progresses. Yeah? How's the temperature in here? I can feel the heater blowing heat. Is it warm? You crack it. Is it okay? Is it warm? A little bit too warm? I'm gonna crack it a little bit. I'm gonna try to crack the door anyway. Oh, much cooler up here. Alright. Cool. Excellent. Let's mute this for a moment. Start and stop the camera.